In the previous video, I introduced the idea of what work is from the energy framework. In this video, I want to get more specific in terms of what is the actual physics principle which you can use to figure out what's going on when you're talking about work from the energy framework. And where pretty much every physics course and every physics textbook will start usually is what they call the kind of overall main principle here is called work-energy theorem, or sometimes people call it work-kinetic energy theorem. And that principle says a very, very simple, very, very concise formula, which is that the work done on a system equals the change in the system's kinetic energy. And that incredibly compact result is the key point of understanding work from the energy framework. Now, I feel like the standard physics textbook just kind of ends the explanation there. But for me personally, I could never wrap my head around how this could be the main idea of this work energy section, because I just showed in the previous video how sometimes work is the change in kinetic energy, sometimes it's the change in total energy, sometimes it's the change in potential energy, and really it's just a transfer of energy. So what does this formula really mean? What is it actually saying? And how is it consistent with all the things that I talked about in the previous video? Because I clearly showed you an example in the previous video, the one where you lift the box up like this, where the box's kinetic energy did not change, and yet there was work done. And that's because of one important caveat to this formula, which is that this formula only applies when you are talking about the total network done on an object, the total network done by all different effects done on the object combined. If you are doing the total work done on an object, it is this simple, and it's just the total work done is equal to the change in kinetic energy, period. That's it. But when you're actually doing problems as a student, or when you're actually trying to understand specifics, it's not always that simple, which is where this gets kind of confusing to me. So let me show you how this can be true with the examples that we did in the previous case. Now, personally, I like to give some further explanation beyond just work-energy theorem, and this is really just me. You won't really find this in any physics textbook, but in my view of this, there's kind of three cases you might be doing, okay? Case number one, you might be considering the total network done on an object, in which case it's the change in kinetic energy, and that's perfectly fine. I'm not saying that's wrong, but that's not always what you're calculating in a given problem. Another thing you might be doing, and let me just emphasize that case number one here, the case is when you are calculating the total net work done on an object. So case number two, we saw in the previous video how there was one case where we had the work done equal to the change in the system's total energy. Okay. My personal terminology of how I wrap my head around this, and again, this isn't like standard terminology that everyone in physics uses, so just be aware of that. But I like to call this external work done on the system. And what I mean by external work is this equation can be used when you are talking about the work done on a system from outside, and by outside we mean outside of any sources of energy that you are already keeping track of. It's a little bit hard to put this in words, so sorry if it's a little bit confusing at first. But what I'm saying here is, well, maybe I'll give you case number three, and it will become a little bit more clear by giving the opposite. The other possibility is we can have what I refer to as internal work, in which case it's minus delta U. That was the third formula given in the previous video. And in this case, you're doing the work done on a system from within, and by that I mean within the types of energy that are already being tracked by you. Okay, so let me explain this now that you can kind of see the three cases. What I mean is that there's basically a few different possibilities. You can have a transfer of energy just between the kinetic and potential energy, but since you are already keeping track of the kinetic energy and you are already keeping track of the potential energy, if you transfer energy between the kinetic and potential forms, it's not going to change the total energy of the system. The kinetic energy will go up and the potential energy will go down, or vice versa. They will change by the same amount. So you will get a positive change in kinetic energy, but a negative change in potential energy, or vice versa. And so the way you can keep track of that amount of work most easily is look at the potential energy of the effect that you are currently looking at. So for example, if you want to know the work done by gravity, look at the gravitational potential energy. If the gravitational potential energy goes down, that means the kinetic energy must have went up. So you have a positive work being done if the gravitational potential energy goes down, and you have a negative work being done if the gravitational potential energy goes up. So in other words, you look at the potential energy, and by conservation of energy, you know that whether that goes up or down, that means if it goes up, it means energy came in to the potential energy, and if it goes down, it means energy went out of the potential energy into something else. The other case is maybe you're not keeping track of this type of energy in your potential energy, like in my example in the previous video where we lift the box up. Conceptually, the reason why energy is not conserved here is because I'm not keeping track of the energy in my body. Where the energy came from that caused the energy not to be conserved is that it came from my own body. I transferred energy into the box, me being like an outside force that is not included in the equations. And that's why energy is not conserved, because I didn't include it in the equations. You know, you can't just say like, well, conservation of energy applies, so therefore the initial energy always equals the final energy. Well, that's only true if you're omnipotent and you include every possible type of energy in the initial energy and every possible type of energy in the final energy. In many, 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 many practical cases, you don't know the total amount of initial energy. You don't know the total amount of final energy. So they're not necessarily equal to each other. It's because of your ignorance in your ability to keep track of all the energy in the universe. But it can appear that that changes the total energy of the system. And that's what I refer to as external work. It's external to the things that you're keeping track of. Whereas if the transfer is internal to the things you're keeping track of, it might not be changing the total energy of the system. It can just be a transfer between kinetic and potential forms. The analogy I like to use to try to wrap your head around this is imagine that you have a savings account and a checking account at your bank. Okay, you have a savings account and a checking account. Now, you want to know, work is basically like the amount of money that the account is changing by. Work is like a transfer of money from one account to another account. So there's a few different ways that these transfers can happen. One type of transfer, and this is case number 2, an external transfer, is like you get paid from your work and they transfer money into your checking account. This causes your checking account balance to go up, and it also causes your total net worth to go up. You know, both simultaneously. So the checking account balance is like your kinetic energy, and your total net worth, the sum of your two balances, that's like your total energy in the system. The other possibility is you might like transfer some of the money from your checking account into your savings account, but your bank balances will change when you do that, but it doesn't change the total amount of energy that you have. because when your checking balance goes down, your savings balance goes up by the same amount. And if you do the transfer the other way, your checking balance goes up, but your savings balance goes down. So you have an internal transfer between your two accounts. This is not going to change the total amount of money that you have, but it is going to change the individual balances of the two accounts. So if you just have your eye on your checking account, you can make the statement that, well, if I keep track of all transfers into my checking account, the change in my checking account balance will be equal to the total of all those transfers. That's case number one. Case number two is whatever money I transfer into my checking account from outside is going to increase the amount of money that I have. And statement number three there is if I'm doing internal transfers between checking and savings, when one balance goes up, the other one goes down by the same amount. So instead of checking the checking balance, I can just look at the savings balance and put a negative sign in front, because if the savings balance goes up, that means the checking must have gone down and vice versa. Okay, so that was a very long-winded explanation for just a point that I consider to be weird and confusing, where if you read a physics textbook, it will just say work is equal to the change in kinetic energy done. But that means that they're only considering the case of the total work done on the system from all different sources, both internal and external to the system, in which case that's a perfectly fine system to make. But if in a given problem, you're calculating something more specific than that, be a little bit careful of make sure about what you're calculating. Are you actually trying to calculate the total work done on the system, or are you looking at an individual transfer? Okay, so let me end this video here, and I'll do another video where I use this idea to explain the two examples that I showed earlier.